Hello everyone. Let me introduce myself. I am Sajna Hameed. I am a mathematics teaching professional. Today I would like to discuss with you all one of the very important concept in geometry. That is nothing but circles. So before entering into the nuances of this particular beautiful concept, I would like to ask you, what do you understand by the concept circle? What it is exactly? As far as geometry is concerned, what is exactly a circle? Okay, many of you, most of you, I should say, must be interested in stargazing, right? So I would like to ask you, on a very bright night, you just think about that you are, seeing or you are viewing a sky studded with stars. Okay, so what I'm going to do is, I would like to select the most brightest one from the sky, right? So always remember it's a plane and I have chosen the brightest star from the sky. But now I need to select a few more stars from it. So what I am planning is, I will just keep some clause. The clause is nothing but I am planning to select a few more stars from the sky with the condition that the stars which I am going to select, okay, must be at same distance from the one which I have already chosen. Okay, okay, that process is also done. I have selected stars based on the condition I have chosen. Now, the locus of all those stars I have selected, if I try to take the collection of all those stars, keeping the brightest one at the center, so that the distance between the one which I have chosen from the other stars, okay, and the center one would remain the same. Okay, then when I take the locus of all those, I can see that I get a closed shaped figure that is nothing but a circle. So I would like to reiterate the center which we have chosen, the brightest one we have chosen is nothing but the center of the closed figure, that is nothing but the circle. And the same distance which we told, which I have already mentioned at the beginning, the distance between each star and the one which I have already chosen, that is nothing but is going to act as the radius of the closed figure circle. So I think you would be able to visualize when I talk about a star-studded sky, the brightest star chosen, then I would like to select few more stars, and when I take the collection or the locus of all those stars, we can see that we will get a closed figure that is nothing but a circle. So in that particular aspect of geometry, I would like to discuss a very important theorem or a property, I can say, about circle today. Okay, that property is nothing but, I will just say the statement of that. See, let me draw a figure first for the circle. Okay, this is a circle with center O. So we always know that whenever we, want to label a particular circle, we will label it as, with the help of a particular variable that is that denotes the center of the circle. So this is circle O. Okay. So what I am trying to say today is, how they discuss with you today is a property based on circle. So it is called as circle theorem actually. Let me write it. It is nothing but circle theorem. So what the circle theorem says, the statement is an angle subtended by. So before entering into the angle subtended by, I would like to ask you, what do you understand by the terminology angle? What is an angle actually? So we know that angle, for getting an angle, we need an initial ray, right? So we need an initial ray for getting an angle. So the extent up to which this particular ray rotates, isn't it? You will get an angle. Let me label it as theta. So what is an angle actually? The extent up to which an initial ray rotates gives you an angle. So here in this context, what I'm going to say is the angle subtended by an arc at the center of a circle. So let me take an arc here. Let me take it. What is an arc of a circle? An arc of a circle is nothing but a parted portion, okay, or a portion. So let me label this arc as AB. So the angle subtended by this particular arc at the center of the circle, that means I need to join it like this, right? So this is the angle. This is the angle. This angle AOB is the angle subtended by this particular arc at the center. is always 2 times, or we can say double, the angle subtended by the same arc on any other portion in the remaining part of the circle. So when you talk about that, let me ask you, if I take this particular portion as a minor arc, what about this portion of the circle? That is nothing but the major arc. Okay. So if this minor arc AB subtend an angle AOB at the center, the arc subtended by the angle subtended by the arc AB at the center will always be 2 times the angle subtended by the same arc on any other part in the remaining portion of the circle. That means if I take another angle here, let it be APB. So according to the theorem, what it says, angle AOB is nothing but 2 times angle AP. That is what the theorem says. Let me tell you once again, the angle subtended by an arc at the center of the circle, that is nothing but AOB, this angle, will always be 2 times or double the angle subtended by the same arc on any other portion in the remaining part of the circle. That means AOB is nothing but 2 times APB. For example, with the help of an angle measure, I can tell you if this central angle is, or if this portion of the angle, which one, APB is 60 degrees, what about the central angle then? Central angle will obviously become 120 degrees. Or I can ask you the reverse. If this central angle, suppose if this is going to be 110 degrees, what about APB? Half of the central angle, it will be 55. But now what we are trying to do today is, I'm just going to explain you the proof of this. How can we prove it? How can we say that the angle subtended at the center will be 2 times angle subtended by the same arc on any other part of the portion or the circular portion? So how can we prove it? That is what we are going to see now. So in this first part, actually what I have taken is I have considered AB as a minor arc, and with the help of that minor arc on any other portion, we are going to see angle will be half of the central angle, or the central angle will be 2 times the angle subtended by the same arc on any other portion. So for that, what we are doing is we are trying to prove it. Okay, let me drop in a line passing through the center, and let me label it as PE. Okay, and now you can see a triangle POB here, POB. Okay, I am going to write the angle BOE as 1. So what is this angle 1? Like what this angle 1 acts for the triangle POB, it is very clear that angle 1 acts as an exterior angle for the triangle POB, right? So let me label this OPB as 2 and this PBO as 3. So can you tell me any peculiarity for this triangle POB? What type of an angle, what type of a triangle is that? Triangle POB, obviously we know that it is an isosceles triangle. Why? Because OP and OB both are acting as a radii to the circle, right? So both are the radii, that means POB is an isosceles triangle. So just recollect the property of isosceles triangle we have learned. When two sides of a triangle are equal, that triangle is called as an isosceles triangle. So what about their base angles or the angles opposite to those two sides? That is angle 2 and angle 3 will become equal in measure. These all properties we have already learned. Okay. So keeping that in view, from that triangle, which one? POB, we can say that OP is equal to OB, which implies we can say angle 2 is equal to angle 3. No doubt about it. Now, applying the exterior angle property for angle 1, how can you express angle 1 here? Angle 1 is nothing but angle 2 plus angle 3. So I can write exterior angle 1, that is angle 1 is nothing but BOE, right? Which is equal to angle 2 plus angle 3. Since these two angles are equal in measure, I can write angle 1 as 2 times angle 2. Why I am writing 2 angle 2 instead of 2 angle 3? Because I need to show that AOB is 2 times APB. So 2 is the angle which is related with the point P. So I am writing instead of 2 angle 3, 2 angle 2. So let me write it as 1. Okay, now coming to this triangle POA. Okay, you can see an exterior angle here. Let me label it as 4. Okay, and this angle OPA, let me label it as 5, and OAB, let it be 6. So in a similar fashion, can you tell me POA is nothing but an isosceles triangle because OP and OA both are radii, and we know that for an exterior angle, it is equal to sum of the two opposite interior angles, that is 5 plus 6, and being an isosceles triangle, 5 equal to 6. So how can you write angle 4? Angle 4 we can write as, in a similar fashion, we can write as 2 angle 5. So this is going to be the second relation, second equation between angle 1 and angle 4. So now what I want is, I want AOB. What is angle AOB? Angle AOB is nothing but angle 1 plus angle 4, right? Angle 1 plus angle 4, which is going to be, what is angle 1? Angle 1 we already got as 2 times angle 2. And what is angle 4? Angle 4 we got as 2 times angle 5, which is equal to 2 times, what is angle 2 plus angle 5? It is equal to 2 times angle 2 plus angle 5 is nothing but APB. 2 times angle APB. So in that way, we have proved that the central angle AOB is equal to 2 times angle APB, or the angle formed by the same arc on any other part in the remaining portion of the circle. So this is a very important theorem, because being MCQ, then you can expect for the the board exams and all, the different types of questions actually board can frame and can come for the exam as well. So be very clear. Always remember the central angle will always be 2 times the angle formed by the same arc on any other part of the circle. So this we are proving with the help of a minor arc. In a similar way, we can prove keeping AB as a semicircle, and in the same way, we can prove keeping AB as a major arc as well, as a major arc also. So now, with the help of this, we can get one more result. See, if this AOB is 2 times APB, so if I take another angle, keeping AB as the arc, if I take another angle, let me take this angle as, it's not passing through the center, let it be Q. So what can you say about angle P and angle Q? Are they going to be equal? Always remember this minor arc, this, see the tip of this arc, A and B. Okay, A and B forming a central angle AOB. Same time A and B forming another angle AQB in the remaining portion of the circle. So whatever be the angle is for APB, the same angle will remain for AQB as well. Okay, if central angle is going to be 120, what about APB? APB will be 60. And what about AQB? AQB also will be 60. So the result follows is angles in the same segment of a circle are equal in measure. Angles in the same segment of a circle, as far as this particular concept is concerned, in same segment is nothing but APB as well as AQB, and this is the arc with the tip A and B. Segment, as we all know, how can we explain a segment, or how can we define a segment? A segment is nothing but the portion or the region between, yes, an arc and the chord. That is nothing but if I join a chord here, region involving this arc and that particular chord will be the segment, that is a minor segment, and the remaining all will be the major segment. Sector, as you all know, the portion or this particular region between the arc and the two radii will be the sector of this circle. Those are our basic concepts which you must have learned in the junior classes. Now I would like to explain one more concept here. One more with the help of the same property. What I am trying to show you here is, how can we say that angle in a semicircle is 90 degrees? Okay, so the same circle with the same property here, instead of this here in this context, we have taken this as a minor arc. Okay, we have taken this as a minor arc. Now let us see if I consider AB as a semicircle. This is A, this is B. Okay, this full arc is going to be a semicircle. This is a semicircle. Now, as far as the theorem is concerned, what the statement says, angle subtended by an arc at the center. So, angle subtended by this arc at the center O, that is this particular arc, will be always 2 times angle subtended by the same arc on any other part. So, the remaining portion is here only. So let me take another angle here and let me label it as P. So this AOB is going to be 2 times APB, right? Or this APB is going to be half of AOB. Since look here, AOB is diameter, it's acting as a straight line. So what about this particular angle here? Undoubtedly, we can say it is going to be 180 degrees. Okay, if this AOB central angle is 180, what can you talk about the angle at P? It is obviously, no doubt, this is going to be 90 degrees. So in that way, it's a result followed with the help of this theorem. We can say that angle in a semicircle is always 90 degrees. Angle in a semicircle, angle in a semicircle is always 90 degrees. That is the particular result followed from the main theorem, the circle theorem. Hope these two concepts are clear for you. Let me reiterate. It's a very important concept. You all have to be very thorough with. If the angle in the other side is given as suppose some 90 degree, or that is going to be a semicircle. Suppose it is around 125. So exactly double will be the central angle, or the central angle is given. Always remember half will be the angle in the other part. Okay. Then angles in the same segment of the particular circle will be equal in measure, and angle in a semicircle will always be 90 degrees. So I hope, and we will be doing further problems based on this particular concepts and results in the next class. Hope it's clear for you. If at all any doubt is there, you can clarify the doubt in the next class. Okay. Thank you, children. Thank you.